Hello everyone. From today, I'll cover chapter 4, rigid frame. Rigid frame means connection is rigid. Rigid frame does not mean member is rigid. In chapter 1, 2, and 3, we covered isolate member, but this chapter 4 cover whole system, rigid member. So there is interaction between adjacent member. This beam interact this column interact this beam. So we have to consider the interaction between column and beam. Let's consider this portal frame subjected to concentrate load P. So how to calculate the maximum P in order for this portal frame to sustain? There are several approaches to calculate P. So today I'll introduce the approach 1. Approach 1 is we have to calculate PCR, elastic buckling load, and also we calculate PP, plastic collapse load. So after calculating these two, we can capture P maximum. So basically P maximum is related to buckling and yielding. Buckling PCR, plastic collapse load PP. I will cover this issue in this week. Next week, we will study LRFT approach, design approach. So you can calculate maximum P in LRFT design equation. Today, we will cover somewhat analytical approach. Let's look at the approach 1. If we calculate PCR, PP separately, we can capture collapse load P. Consider this portal frame subjected to concentrated load here. Then if you draw this P and delta curve. So if this system is perfect, we can get this PCR, critical load, buckling load, and you have this displacement line. So this perfect system, we have to do eigenvalue analysis or bifurcation analysis, right? So if it is imperfect system, we have to do load diffraction analysis. So load displacement like that. If we do plastic analysis, then we can get the plastic collapse load here. If we consider this, the PCR consider geometric nonlinearity. PP consider material nonlinearity. If we consider these two at the same time, we can get this curve, failure load. This curve is a realistic curve. Curve consider inelastic second order effect. We call it the inelastic second order analysis or nonlinear inelastic analysis. So as long as we get PCR and PP, we can calculate PF. PF is failure load. So Merchant-Rankine suggests this equation. If you draw this equation, PF PCR 1.0, PFPP 1.0. Okay, the curve is linear like that. So Merchant-Rankine suggests this failure curve. From this equation, if you divide by PF each side, then you can get this equation. So as long as you get PCR and PP, you can get PF approximately. Okay, let's look at the PCR first. How to calculate elastic buckling load of frame, rigid frame. Let's cover PCR first. In analytical approach, how to calculate this PCR? There are three ways. Differential equation, first one. Second way is slope diffraction equation. Third one is matrix stiffness method. Do you remember when you analyze the column? In the case, we firstly use the differential equation, right? Yeah, but this kind of portal frame, if we use the differential equation, it becomes much complicated. So I show you some realistic two methods. One is slope diffraction equation. Other one is matrix stiffness method. In order to get PCR first. Among PCR and PF, we will get PCR first. Later on, we will get PP. The procedure to get PCR PP is analytical approach. After that, we get PF. It is just approximate approach using merchant ranking equation. Let's look at this braced portal frame. Braced means we consider this brace in order to prevent lateral sway. Okay, so we call it braced frame. Consider the concentrated load on the top of each column. So here, let's consider this. If beam stiffness is infinite, then the bottom of this column is hingy, top of this column is fixed, right? Because beam is infinite, so there is no rotation and there is no side sway because the braced. So it looks like fixed. Fixed hinge. In that case, the effective length factor is 0.7. Do you remember? If beam stiffness is 0, then it behaves like hinge. So hinge. In that case, effective length factor is 1.0, right? So we consider extreme two cases like that. So K factor of this column must be greater than 0.7, less than 1.0. It is related to the stiffness of beam and column. If the moment of inertia of column and beam is identical, then K factor is 0.875. If we know this effective length factor, then we can get PCR, right? I'll show you how to calculate this PCR using slope deflection equation. First, this is just some roughly we estimate the K factor, but I'll cover how to calculate PCR using slope deflection equation. In this braced case first. Okay, secondly, I'll show you some unbraced case. Okay, unbraced case means we have side sway like that because there is no brace to prevent side sway. Let's calculate the extreme case first. If beam stiffness is infinite, then the bottom of the column is hingy, top of the column there is no rotation, right? Because IB is infinite. But there is side sway, right? In that case, K factor is 2. K, so real part, imaginary part like that, the hinge, so it is 2L. So K equal 2. If IB equal 0, so that means the rotation is free. There is rotation and there is side sway also. So it is unstable structure. Free rotation and then free side sway. So unstable means K factor is infinite. So the range of K factor is greater than 2.0, less than infinite. If IC and IB, in that case K equal 2.33. I'll show you how to calculate this value using slope deflection equation first. Let's look at this one. Slope deflection equation. This is a braced case. We assume braced case. There is no side sway case. This A, B, C, D slope deflection equation sign convention is we consider clockwise rotation. So theta B, clockwise rotation, clockwise moment, MBA, clockwise rotation, clockwise moment, like that. Okay, that is sign convention. So in slope deflection equation, we don't know theta A and theta B. How about theta C and theta D? This structure is symmetric. So theta B equals theta C, theta A equals theta D. So unknown is just 2, not 4. Okay, so we consider left-hand side only. Unknown is theta and theta B, so we need 2 equations to solve theta and theta B. One equation is MAB, moment at A equal 0. Why? Hinge, right? The summation of moment at B, that is MBA, MBC, if you add together, that must be 0. Why? Joint equilibrium. The summation of moment at joint must be 0. Otherwise, it rotates further. Stay there with some rotate. That means joint equilibrium satisfy. MBA plus MBC equals 0, right? Yeah. So we have to make these two equations. Then we can get theta and theta B. Let's look at this one. Let's establish some slope deflection equation. MAB. MAB equal EI over L SII. C means column, theta A plus SIC theta B. Do you remember? We already learned this one. How about then MBA? MBA is EI over L theta IJ C theta A plus theta SIIC theta B, like that, right? Then MAB equals 0, right? Because it is hinge. There is no moment at hinge. From this equation, you get the relationship theta A equal minus Sij blah blah blah, right? If you input this equation into here, your MBA equation can be written as this. So you already use one condition, MAB equals 0, right? And let's look at the beam, this one, MBC equal EI over L SIIB. B means beam, theta B, Sij theta C. As I mentioned before, theta C equal minus theta B because it is symmetric. So if you input theta C here, then you can MBC equal this equation, and this beam case SII 4, Sij 2. So EI over L theta B. And again, the equilibrium MBA plus MBC. Here, MBA, MBC must be 0, okay, due to joint equilibrium. So MBA is this equation. MBC is this equation. Then you can write this equation, right? So from here, you can write this form from table 3.7. You remember there is SII value, Sij value corresponding to KL, right? Using table 3.7 in your book, in order to satisfy this equation, you have to input this value and this value by trial and error procedure. Then you can find out somewhat approximate SII, Sij value, satisfy this equation. In that case, KL 3.59. So you have to use this table. Then that is square root 2 K equal PEI. Okay, this is small k. This is different, small k and large k. Small k equal square root PEI. That is small k. K equal effective length factor. Then this one equal 3.59. From this one, if you make the square, then you can get this PCR, 12.9 EI over L square. If you know this PCR, you can get K factor, effective length factor, from this equation, P over PCR, 875. Okay, it is the same as we have seen, right? That is a procedure. Let's look at the unbraced case. Unbraced case. In this unbraced case, we have the side sway of delta, right? The unknown equal theta A, theta B, and delta. We have three unknown, so we need three equation again. So MA equals 0. The summation of the moment at B, joint moment, equals 0. That means MBA plus MBC equals 0. And then how to get the another equation is that the shear force at this top equals 0. Why? There is no lateral load here. So we don't know any shear force here. So if we consider this shear force can be calculated. If P here, P, and MBA here, then if you take the moment here, clockwise MBA, P delta, right? And minus the V times L, right? Equal 0 from equilibrium. From that equation, the shear force equal MBA plus P delta over L. We can represent V as a term of MBA P delta, but there is no external P here, external load here. So the shear force must be 0. So this represented shear force equals 0, right? Yeah, so we have three conditions. So then conceptually, we can this form as this kind of matrix form. So unknown is zeta A, zeta B, and delta, and then we have some terms here in this matrix equal to 0, 0, 0, 0, 0, 0, 0. We can write in this matrix form if we solve this simultaneous equation. So here, in order to satisfy 0, 0, 0, determinant of this matrix must be 0. From this equation, you can get KL equal 1.35. From this on, you can get PCR 1.82 EI over L square, and then you can get effective length vector 2.33. It is the whole procedure in this unbraced case. From now on, I'll show you somewhat detailed procedure. Yeah, sway permitted case. Sway permitted case. I just follow your book. Here, MAB, column AB. A is column bottom, B is column top. Okay, MAB equal slope deflection equations SII, zeta A, Sij, zeta B. We have side sway delta. In that case, we can write like this: SIC, Sijc, delta of L, C, column length. Okay, that is the equation. How about MBA? We can write this form. So the first condition, MAB equals 0. Why? It is hinge equals 0. From this equation, you can get the relationship zeta A equal blah blah blah. If we input that equation into here instead of this zeta A, then you can rewrite this MBA in this form. Let's get MBC. B is left hand side, C is right hand side. In case there is no side sway, so we don't have any this term. And SII, B, zeta B, Sij, zeta C, like that. Then zeta B and zeta C, they are identical. So we can rewrite this terms of zeta B. Again, zeta IIB is 4, Ij equal 2, right? Yeah, because there is no axial force. In that case, 4, 2. Then we can rewrite this simple form. So 6. Like that. So we get the MBA and MBC. So we can establish joint equilibrium. MBA, MBC plus must be 0 due to joint equilibrium. If you see MBA is this one, MBC this one. This one plus this one equals 0. So you can rewrite the equation like this. You consider story shear equilibrium. You can consider this shear force here. You can also consider shear force here. It is internal shear force, right? But there is no external shear force. So the internal shear force, this one plus this one, must be 0. We call it story shear. Shear force in this story shear equilibrium. So this one plus this one must be 0. So here MAB, MDC, what is that? Hinge. Okay, must be 0. MCD, MBA is anti-symmetric condition. We can rewrite this equation into this simple form. So ultimately we get this equation. MBA, you have the equation, the previous page, you input this MBA like that. So you have the equation, this equation, and then previously this equation, right? You have two equations. Then you have two unknown, zeta B and delta, because zeta A already eliminate through that simultaneous equation. Okay, so zeta B and delta, you have two unknown here because you already eliminate zeta A through the equation operation. So those two equations can be write this matrix form regarding zeta A and delta. S means this one. So we just write this simple form. Here we assume IB and IC equal I. The moment of inertial beam and column is identical. Okay, I. Length LB and LC, column and beam also identical L. Then this equation can be written like that. Let's calculate K factor in this case. So in order to satisfy this equation, this determinant must be 0. This must be 0. You can get some equation, right? This one times, yeah? Multiply this one, minus multiply, and this one, right? And then again, if you use the table 3.7, you can get the value KL, okay? KL equal 1.35. So PCR equal 1.882. That is procedure. You get the PCR. Do you understand? Let's finish first lecture of this week. Bye.